Hey guys, Mr. O'Sullivan here. Hey, we're continuing to talk about differential equations, and now we're going to tackle um, exam from 2007, question number 5. And so we're given, consider the differential equation dy dx equals 1/2 x plus y minus 1. Part A says, on the axes provided, sketch a slope field for the given differential equation at the 9 points indicated. Part B says, find d2y dx2 in terms of x and y. Describe the region in the xy plane in which all solution curves to the differential equation are concave up. Part C says that y equals fx be a particular solution of the differential equation with the initial condition f at 0 equals 1. Does f have a relative minimum, a relative max, or neither at x equals 0? And then justify your answer. And then part D says find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, so let's go ahead and jump in. So part A, hopefully is going to be a confidence builder. Just want us to sketch the slope field on the axes provided. So we're looking at these 9 points. It's red, so it kind of stands out a little bit more. So these 9 points. Two, three, 4, 5, 6, 7, 8, 9. And so then basically, all I'm going to do is I'm going to take the coordinates for each point and plug it into my differential equation, and then see what the result is. And that result is going to be the slope of the small tangent line that I'm drawing. So I'm not going to put the coordinates for all the points, but I will just for a few, just to kind of illustrate. So this point right here, the coordinates for that point will be 1, 0. So again, I'm going to take the 1, put it into the x in my differential equation. So it's going to be 1/2 times 1 is 1/2 plus 0. It's going to be 1/2 minus 1 is going to be negative 1/2. So I want to draw a tangent line that has a slope of negative 1/2. So, and again, these don't need to be exact, but if I draw this one, if I sketch it kind of from just kind of sketching it, if I kind of line up that point right there like that, well, that would be a -1 slope. So I don't want to be as steep as that. So I want to kind of just sketch it maybe more along those lines. And so we could say that little small tangent line there just has a slope of -1/2. Okay. Okay. So there it is, -1/2. And that was the slope that I wanted, was -1/2. Just checking that because that's going to be 1/2 plus 0 minus 1 would be -1/2. So that should have been -1/2 is the slope of that tangent line. Okay. So if I lather, rinse and repeat for each one of these other, if I do this one next, looking at that, that has coordinates of 1, 1. So if I plug that into my differential equation, it's going to be 1/2 plus 1 minus 1. So that's going to should have a slope of positive 1/2. So if that's -1/2, I'm just going to sketch it. So that would be positive 1/2. Go to the one right above it. That has coordinates of 1, 2. And if I plug that in, that's going to be 1/2 plus 2 minus 1. So that's going to be 1/2 plus 1, or 3/2. So that is going to really be a steeper slope line like that, with a slope of 3/2 or 1 1/2. Okay, move over here. Okay, all three of these points, the x coordinate is going to be 0. So for this point on the x-axis, plug that in. Its coordinates are the origin 0, 0. So it's just going to have a slope of -1. So slope of -1, the one right above it, coordinates 0, 1. So I plug that in, and that's just going to have a slope of 0 plus 1 minus 1. I'll have a slope of 0. So just a horizontal tangent line right there. And then this one right above it, plug that one in. That has coordinates 0, 2. So that's going to have a slope of positive 1. So yeah. Okay. All right, now I move to my last three. These all have coordinates of x equals negative 1. So I plug in my coordinates at this point, has coordinates negative 1, 0. Plug that in, and my slope should be negative 3 halves. So line that up. That. Move to the one right above it. Has coordinates negative 1, 1. Plug that in, and that should have a slope of negative 1 half. And the last one, plug in the coordinates negative 1, 2. So that's going to be, should have a slope of positive 1 half. Okay, and there's my slope field. Okay, and if I kind of take a gander at that, that should have some kind of sort of symmetry to it. I can see here negative 1 half, 0, positive 1 half. If I go along this top row, my slopes are 1 half, 1, 3 halves, kind of increasing as I'm going to the right. And then as I look in that bottom row, negative 3 halves, negative 1, negative 1 half. So again, my slopes would be increasing as I go to the right. Okay, so that looks pretty good. Part B says find the second derivative in terms of x and y, and then describe the region in the xy plane in which all the solution curves to the differential equation are concave up. Okay, so first order of business, I want to find the second derivative. So I'm going to do my work for this one right here. So I'm going to take dy dx is equal to 1 half x plus y minus 1. Okay, and then what I want to do is I want to do ddx of the entire equation. So when I do that, on the left side, I'm going to get the notation for the second derivative, d2y dx2 is equal to, and then as I do ddx on each one of the three terms on the right side, ddx of 1 half x is 1 half, ddx of y will be dy dx, and then ddx of negative 1, which is a constant, is 0. Okay, well, I'm not done yet because they said find the second derivative in terms of x and y. I have the second derivative just in terms really of dy dx. So what I have to do is I have to do one more substitution. I need to take this, and I'm going to substitute in what dy dx equals. So it's equal to 1 half x plus y minus 1. So I'm just going to rewrite this right side as 1 half, that's my 1 half there, plus 1 half x plus y minus 1. Okay, I can kind of simplify this a little bit, kind of combine my 1 half, my negative 1, and I get second derivative is equal to, I'm going to just write this term first, 1 half x plus y minus 1 half. And I get that actually again by combining the 1 half and the negative 1. Okay, so there's my second derivative. That was the first thing I was asked to do. Now it's asking me to describe the region in the xy plane in which all solution curves to the differential equation are concave up. Well, I know my solution curves are going to be concave up when the second derivative is positive. Okay, so what I'm asked to do is basically I'm looking where this side of my equation is going to be greater than 0. So I'm just going to set that up, 0 greater than half x plus y minus 1 half. And so what I can do now, this is just a linear equation. I'm just going to solve this for y, this inequality. And so I'm going to get y greater than negative 1/2 x plus 1/2. I just move this to the other side of the inequality, and I move that also to the other side of the inequality. So now I have this linear inequality, and I'm basically saying that all solution curves above this line, so really up above the line y equal to negative 1/2 x plus 1/2 will be concave up. Okay, that little second part there was maybe just a little bit tricky on that. Okay, so there's part B. Found the second derivative and also describe the region where the solution curves are concave up. Part C says let y equal f of x be a particular solution of the differential equation with the initial condition f at 0 equals 1. Does f have a relative min, relative max, or neither at x equals 0, which is this initial condition I'm given, and then justify the answer? Well, what I really need to do is I need to check this point, which is x equals 0, y equals 1. I need to check that point in my first derivative and then in my second derivative and just kind of see the results of the value of those two derivatives for that particular point. So if I do this, see my first derivative dy dx is equal to 1/2 x plus y minus 1. 1/2 x plus y minus 1. It's dy dx. And then my second derivative that I just figured out, d d2 dx2 in terms of x and y is right there, 1/2 x plus y minus 1/2. 1/2 x 1/2 x plus y minus 1/2. Okay. And so again, my point that I'm interested in is f at 0 equals 1. Which again, if I want to think of that as a coordinate pair, that would be 0, 1. That's my x, that's my y, just so I don't mess it up. Okay, so now I'm really looking for dy dx such that x is 0, y is 1. So the right side of my equation is going to be 1/2 times 0 plus 1 minus 1. Well, that's going to equal 0. Okay, well, that looks good because my first derivative at that particular point is equal to 0. So that's kind of lead me to believe that I could have a relative max or relative min or neither. So now I'm going to take a look at my second derivative, see what the result of that is at that particular point. So that, again, such that x equals 0, y equals 1. So that's going to look like 1/2 times 0 plus 1 minus 1/2. Okay. Well, if I work that out, that's going to be 0 plus 1 minus 1/2. I don't even really care what that is. I just know that that's going to be a positive value. So that means my second derivative is positive. And so therefore, that means my function, and that also means my, that kind of goes in hand with what I just found in B, that my function is concave up. So if that second derivative is positive value, that must mean that there is a relative minimum. So I'm selecting it's a relative minimum at x equals 0. This is Yeah, on f at x equal to 0. Okay. And my justification is right above that. The value of my first derivative and my second derivative at that particular point. Okay. All right. Part D, last part here. Okay, this one says, find the values of the constants m and b for which y equals mx plus b is the solution to the differential equation. Okay. So let me copy this down below. Have something to look at. Okay. All right. Well, one way I might have looked at this and said, well, gee, can I go back up to the differential equation and just kind of find the particular solution and then kind of just force it to this, to match kind of this linear equation that I'm given here. That's got to be some kind of linear equation, and I just got to find really the value for m, the slope, and b, the y-intercept. Well, issue with that is I'm not really given the initial condition that I could plug in to kind of approach it that way. Also, if I look at this differential equation, it doesn't look like it's going to separate nicely into like the y and dy and the x and the dx. So I'm kind of up against a rock and a hard place going down that road. But what I can do is this. I'm going to just copy my differential equation, dy dx. So dy dx is equal to, I got it right above there, 1/2 x plus y minus 1. Okay, well, what I'm going to do is I'm just going to take my differential equation. I'm going to make a couple substitutions. I know that dy dx is going to have to be my slope. Well, and if I'm not sure of that, one way I could do that is say y equals mx plus b. And, instead of like integrating the differential equation, what I could do is I could like differentiate the particular solution. So that's kind of what I'm doing here. I'm just going d dx of this, and I'm getting that dy dx is equal to, well, d dx of mx is just going to be m. And so really I've just found that, dy dx is equal to m, which should be no surprise because that's just telling me that my derivative is the slope in a linear equation. So I'm taking this and I'm going to make this substitution, dy dx is equal to m. And now I'm going to say that for this y right here, I'm going to substitute mx plus b. So I'm going to have 1/2 x plus mx plus b minus 1. Okay, and again, that's my y. Okay, so I hope you're tracking that. Now what I'm going to do is I'm just going to kind of lose my parentheses. So 1/2 x plus mx plus b minus 1. And I'm going to kind of factor by grouping. This is still equal to m. So m is equal to, now I'm just going to factor out an x. X times 1/2 plus m plus b minus 1. Okay, now right here, what I can do is I can look and say, you know what, m is going to be some constant. It's not going to be in terms of x. So that tells me right here that this term right here has to zero out. And in order for this to zero out, that means that 0 is equal to 1/2 plus m. Okay. That also tells me that if this term zeroes out, if I ignore that, that tells me that m is equal to b minus 1. Okay, now I've got two equations right here and I can solve. So I can subtract 1/2 from both sides.
So m is equal to -1/2. And now I can take that information, plug it in over here. -1/2 is equal to b minus 1, add 1, and I get b is equal to +1/2. So those are my values for m and b. And if I plug that in, I can stop right here, but if I just plug that into my point slope form, I'm sorry, slope intercept form, y equals -1/2 x plus 1/2. That should look familiar because that was our linear equation that kind of gave us above that line there, the solution curves are all concave up. And so kind of would have recognized that from part B. See this equation right here? Look familiar? There it is right there. If we would have seen that and kind of made that connection there, we could have saved a lot of time and just gone straight to that part T. But I want to kind of show you guys that the long way. Hope that helps. Thanks, guys. Have a good one.